Um, okay, find the largest volume of a cylinder that fits into a cone that has base radius r and the height h. Well, let me just change something here. I'm going to denote this height of the cone by capital H. Okay, so what is the question? So the picture is the first thing. If you have a diagram or something you can draw, that is where that's going to be very helpful. I have a cone. Here I'm assuming that the cone is the right cone. And I want to fit in a cylinder, circular cylinder, and I'm trying to maximize that. Well, what does it mean? It means that, well, I want to fit this guy, something like that. But here, what is important is that the radius of the base of the cone is given. It is capital R. The height of that guy is also given. It's capital H. So we have a fixed cone. What we can change is that, okay, I can change and try to fit different cylinders inside this cone. The question is that which one of these cylinders is going to give me have the maximum volume? Well, obviously, for example, I can fit in this guy here with high very high height, but very small area in the base of the circle. So the changing those two would change everything. So here, now I'm starting to finding what are the variables. So identifying the quantities. First thing first, well, you can always write that first thing, is that the quantity that we want to maximize or optimize in this case. So the first thing is that volume of the cylinder. And then based on that, we go see what does volume depend on? Volume of a cylinder is the area of the base times the height, yes? So there are two things that will play a role there. One is the radius of the base, or in this case, the radius of the circle based on which we make the cylinder. And then the height of the cylinder. And these, at least to start with, seem what we have to deal with, what we have to work with. And while assign a variables, we are going from the wordings to the formulas, to mathematical models. Everything should be mathematical. Here, I should choose variables. For volume, I choose B. For radius, you see the capital R is used in there, so I would choose lowercase r. And the height, oops, no, I don't want, I don't know what's happening here. Okay. Okay, so the radius of the base of the cone is capital R. I'm going to choose lowercase r for this guy, and for the height, I'm going to choose lowercase h. So for the cone, I'm going to have capital R and H. For the cylinder, I'm using lowercase r and h. Then the second thing is that find the relations. So first, that volume of cylinder is area of the base. In this case, the area of the circle with radius lowercase r times the height. Very nice. That's one important relation that we want to have. We need to have. The second thing is that if I cut this cone, I make it half just from the top point and then cut it vertically, what I will see is this, that my I'll use blue, okay. So if I cut, I will see a triangle. So the cone will turn into triangle. And the guy over here, the cylinder will be some rectangle, yes. If I make this one half, so in other words, if I draw, didn't I choose that? Okay. If I draw the height or the line that goes from the top vertex of that cylinder of that triangle to the base, okay? Now, I know that this guy here is R. I called this piece H. The height of the cone will transfer to that, and the radius of the base will transfer to this thing. Let me write this thing in a nicer place. This is H, so I don't need to see that part. Very nice. Since this, oh God, since that edge and that edge are parallel, because that's the lower and top basically surface of the cylinder. So that means that these two triangles are similar. And when you have similar triangles, you know that the ratio of the corresponding edges are going to be equal. In other words, the base of the lower the smaller triangle over the base of the larger triangle must be equal to the height of the smaller triangle over the height of the bigger triangle. So the height of the bigger triangle is there. But what is the height of the small triangle? Well, the whole thing is h. I throw out lowercase h. What remains up there is going to be capital H minus lowercase h. And then, well, simply I can use that and write h in terms of r, and I can write this like h minus h is equal to r h r, and from there I can see that h minus r h r is equal to lowercase h. Why is it important? Because now I can take that h and plug in into that formula for v and write v as a function only in terms of r. So here it will be pi r squared times h pi r squared times h here for h. I'm writing this h minus r h r. I have that, and that is function of r. Very nice. Okay, and you look at this function, you say that I'm done almost because this is a function I want to maximize. But in the optimization problems, you have to always determine what is the domain, the physical domain, or the problem-related domain, not the mathematical domain, the problem-related domain for R, or for your variable here. So that's the third thing we are going to do, the real-world domain for the variable, which is R in this case. R must be a positive number. It's because it is radius of some circle there, yes? Well, I'm saying that I'm including R equal to 0 as well. So it must be bigger than or equal to 0. 0 meaning that my circle is going to be just 1 point. How about the upper bound? Well, I can play with this thing. Either use h also must be bigger than equal to 0 and solve it for that. So let me do this one. H is bigger than equal to 0. That means that h minus r h over r must be equal to 0. And that means that r h over r must be less than h. H is constant. I can cancel that positive constant number. And I can cancel those two, and I write that r can be less than equal to r. One other way of seeing that is that when you have this cone here, you can fit in different r's, yes? So for example, we can fit in this cylinder there, yes? Or I can increase that. How far I can increase? I can increase it until the r is the radius of the base of the cone. Well, in that case, there will be no height, but I can assume that the circle is basically a cylinder with the height 0. That's another way of seeing that r, the radius of the cylinder, cannot go beyond the radius of the cone. So here we found that r is in the interval close into a 0 to capital R. Having that means that we have now our mathematical problem. We want to maximize VR, which is this function pi r squared h minus r h over r on the interval 0 r. Here is one of the things that you can use, and that is that, well, this is a continuous function. That's a closed interval. We'll get absolute max and mean. And to find a max and mean, we need to do some works here. So what is that? We need to find the critical point. So for that, I need to find derivative of v. Well, if I use expanded and then differentiate, that will give me easier differentiation. So it will be pi 2 pi rh, the first term. The second term will give me 3 pi r cube r cubed turned to r2 differentiated, and then h over r. H, capital H and capital R are just constants. So we have that. Set that equal to 0. Then, okay, I want to solve that. I can factor out h. I can factor out pi. So pi h 2r minus 3r squared over r. This is equal to 0. Let me do one more factorization. I can factor out actually r. So this will be 2 minus 3r. So this being 0 means that r is equal to 0. H cannot be 0. I already fixed the height. Either that one is 0 or 2 minus 3r over r must be equal to 0. And from there, you see that we have 3r must be equal to 2r. And from there, you see that r must be 2/3 of r. That's one critical point. The other critical points, r is equal to 0. We are only interested in the critical points which are in the interval. This is 2/3 of r, and it is between 0 and r, and r equal to 0, it is already included. So both of them we have to include. Then the endpoints. When r is 0, when r is lowercase r. Now, plug in everything there. So v at 0, if I use this formula, you see that this is pi 0 squared times h minus 0 times h over r. This is 0. V at capital R is pi capital R squared h minus r h over r. These two cancels. H minus h, this piece here is 0, so this will be 0. And v at the critical points here, 2/3 of r. So I have pi 2/3 of r squared times h minus 2/3 of r times h over r. Now we can cancel these r's here, and what I will get is h minus 2/3 of h is 1/3 of h. This is 4 9r squared times pi. So if I want to write that, this is 4 over 27 pi r squared h. In other words, the maximum volume of such a cylinder is going to be 4/9 of the volume of the cylinder itself. But what is important for us, the dimensions. So here, the maximum happens at this point, where the radius is 2/3 of the radius of the bigger one. How about the height? Well, sorry, I should put this one. How about the lowercase height? If I use this formula that I found for the relation between h and r, so put r to be 2/3 of r, and you see that these two cancels, that will give 1/3 of left. So the maximum volume cylinder that can be fit inside a cone of radius capital R and the height of capital H is when the radius of the cylinder is 2/3 of the base, the radius of the base, and the height is 1/3 of the height of the